So I can go through this in order, but any questions up front that you really want to ask? Three. Oh, yeah. All right, so question 3, this is some logic, types of reasoning or fallacies. So you get a problem like this, right? You try to break it into propositions. Usually smaller is better, so you can connect them using things that we know, like implication. So what are the propositions that jump out in this first statement?
All students
in this class understand logic. CJ is a student in class, therefore CJ understands logic. So CJ is a student in this class. It sounds like a proposition. CJ understands logic sounds like a proposition that we're trying to conclude, right? So you could do something like C, and hopefully you write this out. C can be the proposition that CJ is a student. So C is the proposition. You're a student in class. L could be the proposition that you understand logic. And if you do those, you can write this first statement using conditionals. This basically says if you're a student in this class, you understand logic, right? So this first statement is really basically saying C implies L. The second statement says C, and the conclusion is L.
That's correct reasoning.
So that is correct reasoning. What's that called? Yeah, detachment or direct. Did you say direct or correct?
Direct.
Yes, it is direct. I thought you said correct. Yes, it's correct and it's direct. So detachment.
Do you have to write out all the propositions to get it correct? The full points? Or
Well, what did you, well, let's see. Nope, all you gotta do is identify it.
Okay.
But if you don't write the propositions and you identify it wrong, then it's a big 0. So writing the propositions helps. But yeah, all I need to see is the letter here. So I'm gonna turn this into my answer key. So this is direct reasoning. Okay, so what about second question? So C could be, you take the class, and these are not propositions, right? But C is the proposition that you take the class. M is the proposition that you're a CS major. So this says if you're a CS major, you take this class, and Mango is taking this class, therefore Mango must be a CS major. And is that a fallacy?
Yes.
What kind? Fallacy of affirming the conclusion, right? So that's a D, right? And if you think about it, it should make sense, right? If you're a CS major, you take this class, but there could be people in this class.
C.
Say what?
C, not D.
Affirming the conclusion. Thank you. Everybody would have gotten that wrong, right? If you're a CS major, you take this class, but you could be sitting in this class just for fun, right? So Mango's actually a golden retriever, and she might come in just to like hang out, and she's not a CS major, which is good. All right, so that's a fallacy. All parrots like fruit. Marky is not a parrot, therefore Marky does not like fruit. So if you're a parrot, you like fruit. You're not a parrot, therefore you don't like fruit. True or false? Right? Fallacy of denying the hypothesis. So that's D. Marky is also a dog. She likes fruit. All right. Everyone who eats oatmeal is healthy. Eat oatmeal, then you're healthy. Lizzie is not healthy. Therefore, Lizzie does not eat oatmeal. True statement or fallacy? All right, that's got to be true. Because if Lizzie if Lizzie ate oatmeal, she would be healthy. And we just said she's not healthy, so she cannot be eating oatmeal, and that's indirect reasoning. So that's B. Lizzie is a blue-tongued skink, by the way. CJ's the other golden. I used to live with. CJ's actually Mango's son, so they pop up in questions sometimes. All right, does that make sense for 3? All right. Other ones in particular, or should we just go through in order? So let's just keep going from here. Using modular arithmetic or whatever theorems you know, do this calculation. So what did you use for this? What theorems or techniques?
Exponentiation.
Mm-hmm. Modular exponentiation, right? Anything else?
I use Fermat's Little.
You use Fermat's little theorem. Okay, I wasn't sure you could do that, but you can. So you found a multiple of 11 that was close to 515,
Yes.
and then worked up from there.
And I added
Okay, cool. So that works. Probably most people did modular exponentiation, right? One hint is that 515 is close to a power of 2. Fermat's little theorem might get you there quicker. Yeah.
I thought for most little theorem, P needs to be prime.
Oh yes, you're right. P doesn't need to be prime. Yeah. Okay. Yeah. So.
Huh. It still worked. I don't know why.
Did you test the answer?
It was 8, right?
I don't know.
You should hate it.
Yeah.
I got 8 as well.
Yeah. Interesting.
I don't know why.
Okay. All right. So yeah, if we do modular exponentiation, right, it's the sum of 3 powers of 2, and we're doing 122 raised to this power. So we can start off with 122 to the first, and that's just 122. But that's actually just 2 more than a multiple of 12. So 122 squared is going to be congruent to 2 squared, which is 4. 122 to the 4th is going to be congruent to 16, which is 4 squared. But that's also congruent to 4. And now you see a pattern, which is that every other power of 122 is going to be congruent to 4, right? So 122 to the 5/12th is going to be congruent to 4. So 122 to the 5/15th. So it's 122 to the 5/12th times 120, saw what I did, right? Times 122 to the first, which is just 4 times 4 times 4. 4 times
4 times 4 times 2.
times 2, thank you. And 4 times 4 is 16, which is congruent to 4, and so that's congruent to 8. Or you could just go 32 and subtract out 24. What are the first pages of questions? Any issues on the set theory? Modulo, like typos and stuff, that should be straightforward. Let's do these really quickly. This expression is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. All right, so you just add up those squares directly. So I don't know, 1, 4, 5, 9 and 5 is 14, 14 and 16 is 30, 55. That sound familiar? Cool. All right, so this one is the sum from I equals 0 to 3 of the following expression. Well, sum from j equals 0 to 2 of I times j. If j is 0, this is I times 0. If j is 1, it's I times 1. If j is 2, it's I times 2. So it's the sum from I equals 0 to 3. And this expression in here is just 1i plus 2i, so it's just 3i. So now we can expand this summation. So if I is 0, that's 0. If I is 1, it's 3. If it's 2, it's 6. If it's 3, it's 9. So that should just be something like 18. Let's look at that one. So what did you do for this? Did anybody find like the 2-line proof?
It's 6 to the n, anything to the n is divided by 6. And then the 6 modular 1, but I didn't do that on that thing. 6 to any power is still divided by 6, so,
Right.
and then 6 modular 5 is equal
But
to-
divisible by n doesn't mean that if you subtract 1, it's divisible by n minus 1.
So 6 mod 5 is 1, and 1 to the n is 1, and 1 minus 1 is 0.
Yeah, 3-line proof. Right, so 6 is congruent to 1, so 6 to the n is congruent to 1, so 6 to the n minus 1 is congruent to 0 mod 5. Right, this is all mod 5. So 6 to the n minus 1 is divisible by 5. That's the sneakier approach, right? The way we normally do these problems, so we want to know about divisibility by 5, so that says let's work mod 5. And if we work mod 5, we can consider a few possible values for n, right? N could be congruent to 0, 1, 2, 3, or 4. Actually, I don't know if there's a non-sneaky way to do this.
Or you just do the normal table thing.
Yeah, but I don't know if we have that for exponents.
Work for me.
Work
Yeah.
for me, but
Yeah.
only
It works.
because 6 is constant, right?
Right. But, I gotta think about that. Okay. Well, I'll see what you did. But anyway, I think this was the way that I had in mind. But yeah, I'll see what you did. All right. Any truth table issues? Okay, so let's do the proof. If the product of two integers is even, prove that at least one of them is also even. Do not use modular arithmetic. Use the definition of even and odd. So product of an integer times 2, or 2 an integer plus 1. And is this the one we actually did on the board the other day?
Yes.
Okay. So probably you got this without too much issue, but let's run through it really quickly. So proof by contradiction works better here. Because if we start off with a direct proof, we've got a times b equals 2 times something, and then it's not clear how to break that up into statements about a and b individually. But the conclusion is making statements about a and b individually. So so assume that it's not true that a or b are even. Right, negate the conclusion. The conclusion is either a or b have to be even, possibly both. So negate that conclusion that a is even or b is even. And we use De Morgan's without knowing what it's called sometimes. To negate this conclusion, we simply say a is odd and b is odd. Right? If this is true, then neither a nor b can be even. If at least one of a or b is even, it can't be true that they're both odd, right? These are the opposite of each other. But that's really De Morgan's, right? Here we had an or, a is even or b is even. We negate those conditions and we turn it into an and it becomes the opposite. So we assume this. So a is odd and b is odd, so a equals 2k plus 1. B equals 2 times some other integer plus 1. Did anybody use the same integer here? Uh-oh, okay.
Can you, but with subscripts?
You can do subscripts too, yeah. Okay, that's only like 80 points, don't worry about it. So A and B have this form, and if we multiply them, then you do the FOIL, and then factor out a 2. And we've got this extra plus 1 at the end. And this whole thing is an integer because k and j are integers, so we can just replace that with n. And so a times b is 2n plus 1. Therefore, ab is odd. And our hypothesis was that the product ab is even. So that's a contradiction. Therefore, a or b is even. And that basically gets you the proof. So yeah, keep separate versions of this. If you mix them together, right, it doesn't change the conceptualness of it. But sometimes in some of the proofs, people start using the fact that these are the same variable and then taking all kinds of shortcuts. So it's mostly to keep you from going astray. All right, this one you just fill in. So I'm curious about 7 though, and I gotta look and see what you did, because I don't think we can do the following. I don't think that's true. But I don't think we ever talked about this either. So if you tried to do that, then there'll be some partial credit in there. But anybody do something other than this or this?
Table, like what we did,
So what was your thing that you put in the table, values of n?
like n equals 0, 1, 2, 3, 4, 5.
Okay.
Related 6 to the n minus 1.
Right. But I think that's assuming this.
I have a question. How about the n with the negative numbers?
About a what?
N is a negative number.
I don't know.
For example, 6 to the minus 1.
Mm-hmm. If it works for positives, it'll probably work for negatives, but I'm not sure it works for positives either.
I did the table where you have all the modular things, and then I did all those, substitute them all in, so 6 to the power 0 to whatever, and then not 1, and then that 1 minus 1 to 0. But I did it as a table.
Yeah, but as a table, I think what you're probably saying is, for example, if n is congruent to 0 mod 6, then 6 to the n minus 1 is congruent to 6 to the 0 minus 1 mod 6. And that may work, sorry, mod 5. That may work in particular cases, but I don't think we have this in general. Or maybe we do, and I just never realized it. Right, so we know modularly we can add, we can subtract, we can multiply, but raising a fixed number to n, I don't know if that carries over in a modulus. I gotta try it and see.
Professor?
Yeah,
I suppose n should be all the integers now.
yeah, n can be any integer. And normally when we work with tables, what we're doing is we're saying whatever n is, it's congruent to either, in this case, 0, 1, 2, 3, or 4. And so if we show it for those 5 numbers, then we've shown it for all integers. As long as what we're doing over here, modulo 5, carries over to what we're doing on the other side.
If n is negative,
It's still congruent to 0, 1, 2, 3, or 4.
Really?
Sure, because negative 1 is congruent to 4 mod 5.
I mean.
But if you raise it to a power, and 6 to the
6
negative
to the-
1 power, it'll be a fraction.
Yeah, it's
Yeah, that's why I don't think you can do this. Well, we don't even define negative powers for
So totally messed up.
modulo systems, because that assumes we have reciprocals, which we don't always have. All right, so I'll look at that one. That might be one that I made more confusing than I intended to, in which case I'll do something about it. All right, so I'll get these graded up over the weekend and posted, and Monday we will start talking about induction. So watch the induction videos if you haven't already, and we'll jump into that on Monday.